Celine Moreira is the new product development manager with 3+ years of experience in the plastic packing industry and work as a part of the innovation team at Polymateria. She works at Biodegradable additives specially designed for polyolefin, polypropylene and polyethylene, implemented in a wide range of applications such as flexibles, rigid, fibers and non-woven. Her role consists of ensuring that all new products meet technical, commercial and production parameters that require constant engagement in both research and development and commercial department, while liaising with customers to draft product specification reports and testing documentation. She obtained her degree in biological resources from the Institute of Engineering in Porto, Portugal. She also holds a master degree in science in environmental engineering from Cranfield University. Please give a warm welcome to Celine.
Good afternoon. Thank you so much for this invitation. I'm very happy to come and share what the company and myself are doing. I really hope that you enjoy the session. So today, which is the world's first biodegradable technology capable of delivering full biological decomposition of polyolefin packaging materials in the open environment. So who we are Polymateria. We are an advanced tech London-based company that has delivered a technology for biodegradable plastics. We have emerged from Imperial College London's Innovation Hub and we launched the first fully biodegradation technology for polyolefins in 2018. We are based in London, where we then manufacture in France as well. So to start off, it's important to put things into context and why everything related to us started, what was the theory of change, and why the company was founded in the first place. So let's talk about the plastic problem. So essentially, to summarize the global challenges for plastic pollution, out of all the materials or all the plastics produced, 311 million tons are produced per year, in which 233 million tons are other applications, so in the automobile industry, in the coatings industry, in the medicinal industry, whereas 78 million tons goes into your packaging industry. And packaging is essentially all your commodity products, your day-to-day plastics that you find in your supermarket shelves, that you find in your own households. So they're all the throwaway materials that we as a society, we depend a lot on. Out of that 78 million tons of packaging waste, 40% of it gets collected for recycle. It doesn't guarantee that this is going to recycle, it's just that it's collected. Actually, only 2% of all packaging waste gets recycled in closed loop. The rest either get downcycled, and then there's a lot of losses happening during the recycling process. 40% of that gets incinerated for energy recovery. 40% of it still get landfilled. And then 32%, which is where we focused on, is what we call fugitive plastic. So all that waste that essentially escapes the waste management infrastructure. Now these are obviously global values, and they will vary depending on what region of the world you're in. If you're in Europe, you get a higher increase in probably recycling and incineration. If you are in probably regions of Latin America, then there is a higher increase in landfill and fugitive as well, given some areas have a lack of infrastructure and so on. Leakage of plastic And actually 81% of all plastics that get leaked into the environment come from land. And land is the main source of the pollution of plastic packaging that is going into our oceans. So our theory of change was that if we turn off the tap on land and we stop the pollution that is going on land, we can then avoid all the plastics going into the ocean. Because this is significant, and it currently, of all the plastics that already exist in the ocean, there's not much more we can do about it, but we can stop certainly the ones in the future from coming up. And this is especially important because over the next 10 to 50 years, there is going to be an increase in the global polymer demand. And that means there is going to be higher consumption. And to be honest, the infrastructure that currently exists is not going to be able to cope with the amount of waste that we as a society are going to be generating. So when it comes to the landscape, so biodegradation and waste management, there are, for example, when a plastic ends up in the natural environment and gets exposed to all the abiotic factors, then you start getting kind of the physical breakdown of it. So it breaks down into, I would say, into microplastics, and then when you get to that situation, it's a little bit worse. There are some technologies there that, try to overcome this as well, but then it depends kind of on their credibility. When it comes to landfill, so these are anaerobic conditions, it's a managed waste system. However, it's very hard to verify. And then there's also certain landfills that are not managed, so they're not sanitary landfills. And then there's whether that's a landfill or an open dump, can also become a little bit difficult to manage. When it comes to industrial composting, the infrastructure is in order for this waste management system to work. And when it comes to home composting, which is also another managed waste, there's also limitations in the types of applications you can, what types of packaging you can put into this waste. And then comes the biotransformation, which is where we come in. So this is mainly for unmanaged waste. And we call it a new credible and scalable technology. So technically, as I was saying before, 32% of all plastic doesn't get recycled or disposed of properly. And then that leads to your fugitive plastic problem, in which research shows that every year 80% of fugitive plastic on land flows into our oceans. So essentially, how does it work? We technically say that the technology gets divided into 3 phases. So the first phase is the product service line. Then the second phase is the activation. So the activation is mainly triggered by sun, moisture, and air, and kicks off the self-destructing properties.
Celine, just
Yeah?
can you share the screen?
Oh, I am sharing. Is it not sharing my screen?
No.
Okay, let's see. I'll try it. Can you see my screen?
Yes.
Okay, thank you. So essentially, how does the technology work? It's in 3 phases. So the product service line. 2 is the activation of the technology, where this is triggered by sun, moisture, air, and heat. And then this kicks off what we call self-destructing properties. And then 3 is when this plastic then turns into an earth-friendly wax. So a little bit into depth of how the actual biotransformation process works. So it's essentially divided into, I would say, 2 phases. So one is a chemical transformation. So the transformation from that plastic into a wax. And then number 2 is a biological process in which that wax then becomes biodegradable. And that biodegradability is done by the microorganisms and the fungi that exist in the natural environment. However, there's also kind of a stability phase, so a use phase. As a company, we obviously promote as much as possible recycling and reuse, so the 3 R's. So in that phase 1, that storage and use phase, the technology is essentially dormant. So that means it's not activated, it's not going to do anything to the polymer chains. And in that scenario, it can be stored, it can be transported, and then it can be used by the consumer. And if the consumer does the right thing, then it can go into a recycling stream and then back into a new product again. If that scenario doesn't happen, or if that material that gets used doesn't end up back into a managed waste system, then, and it becomes fugitive, so it ends up in the natural environment, like we know most plastics do, then we enter phase 2. And phase 2 is none other than a chemical transformation, where the chains of the polyolefin, so the polyolefin is mainly carbon-carbon bonds, so those bonds then get cleaved, and that then causes a reduction in the molecular weight of the product, and then as well as certain other, the technology has a prebiotic, which will then also introduce new compounds such as ketones and aldehydes, which are known to microorganisms as a food source. So all of this transformation, these cleavages in the carbon-carbon bonds and the reactions with other components, brings that molecular weight down, destroys those plastic properties into what we call then a wax. And that wax essentially has certain chemical properties which no longer represent a plastic, because a plastic will never be able to have those properties. And it's sufficiently very low molecular weight and bioavailable, as we call, because it has the aldehydes and the ketones and all of those components that the bugs like to eat very much. And then you start phase 3, which is then the microbial conversion of a bioavailable wax in the open environment. So this is where you get the biodegradation happening, and then the biodegradation is measured by the amount of carbon that gets converted into carbon dioxide. How do we test this? So this is the specification that we use in order to determine whether or not the plastics that contain our technology are in fact biodegradable. So it's basically a protocol that has a pass-fail criteria associated to stages of testing. The first stage is weathering. So the weathering is conducted to mimic what happens if a plastic ends up in the environment. So you are able to introduce different abiotic processes in a controlled time frame and cycle. Then the ecotoxicity testing is number 2, to ensure that that wax that you have now produced is not toxic in any way. And then number 3 is then the full biodegradation of the wax. This protocol is essentially an umbrella of various international standards, ISOs and ASTM, that already exist, and it basically just groups them together into kind of a protocol for any company or industry to follow. And it's now being adopted in many other countries as well, such as Malaysia and the Philippines and Hungary. So how are we able to test, and how are we be able to prove the biodegradation of our technology? So this testing gets divided into 3 criteria, so 3 phases. The first phase is the chemical transformation. So we measure things like the carbonyl index, so that is the amount of carbonyls that the material is forming, which is basically your carbon-carbon cleavages, and then your reactions forming ketones and aldehydes and all of those other components, and then the reduction of the molecular weight. So we measure different criteria of molecular weight, and then those have to pass these values in order for us to say, okay, this is a wax now. Once we achieve that wax state, then we have to do acute and short-term exposure of the wax to different environments to make sure that it is environmentally safe. So we do Daphnia for freshwater environments, we do earthworms for soil, and we do also seed germinations for different plants to make sure that it's not impacting the reproduction of those plants. Once we prove the wax is environmentally safe, then we do finally the biodegradation of the waxes. So this is biodegradation on soil under mesophilic conditions. So this is open air environments, things that you would find, outdoors in the natural environment, so not defined conditions. All of these tests will have an associated ISO standard to it for the kind of test or method that you're doing. However, for us to be able to define these testing cycles and define what's the correct weathering cycle, what are the correct abiotic factors to provide this material in a realistic manner. So we do use accelerated weathering, but we needed to define the cycle that we use in order to say, okay, this means X amount in the real world. And the only way to prove that is by conducting natural weathering. So that's what we did. We conducted natural weathering of the plastics that contain the technology in different climates, so tropical climate, which is kind of the region highlighted in blue in the map, temperate climates, and then arid or dry climates. So the tropical climates usually represent about 48% of the population, and it's got countries like the Philippines, Malaysia, Indonesia, Brazil, Bangladesh, Mexico, China, a lot of countries that have high leakages of plastic waste into the environment. Temperate climates such as China, Ethiopia, South Africa, Morocco, Spain, Brazil, as well. Temperate climates are known to have big seasonal changes, so you can have very hot summers and then very cold winters. And then your arid or dry climates, so these are regions of North of Africa, parts of Asia, again, certain areas that have a lack in infrastructure for dealing with plastic waste. So we conducted we left our materials in these 3 different climates in order to estimate how the reactions change, so how fast we are able to reach those 3 criteria of molecular weight change and carbon out index. So in tropical, and then we obviously were able to publish this data. So we showed that, in different climates, the reactions will change. Of course, it's normal, but then this all correlates to our accelerated cycle that we use internally or in our labs. But then we are able to say, okay, if you are in a country such as the south of Florida in America, then you will reach this wax stage in 3 months. If you're in a place like the south of France, which is a temperate climate or Mediterranean climate, you'll reach it in 4 months. If you are in the north of Africa, you'll reach it in 2 months. So we are able to give different time frames. The kinetics change, but you're still able to achieve that wax after a very short period of time compared to the conventional plastics, which will just persist for hundreds of years. So how does it work? The chemistry behind this. So on this slide, it shows the different mechanisms of chemical transformation that the technology enhances or turbocharges within the polymer or the polyolefin structure. So then you get the introduction of the keto and the aldehyde groups through the Rishi 1 and 2 reactions. And then the result of this is the significant cleavages of your carbon-carbon bonds, which then lead to molecular weight decrease. This turbocharge or this energy is given by the abiotic factors, so by your sunlight, the moisture, the heat, and the air. These are what then turbocharge that reaction to then cleave those carbon-carbon bonds, and then you get the different compounds being produced, and then those go on to biodegrade. So here's a case study. So this is a polyethylene film containing Polymateria technology. So it was weathered in an outdoor exposure, and then it was given the pass-fail criteria. So this polyethylene film achieved all the chemical criteria that is set out in the BSI PAS 9017. Then that same polyethylene was submitted for ecotoxicity tests, so Daphnia, terrestrial, and earthwormed, and it proved to show no issues at all. And then that same material was then submitted for biodegradation. So the cellulose is kind of the reference material for biodegradation, so that has to reach above 95% in a certain time frame in order for the test to be valid. And then we can see for the polyethylene film, based on the ISO 17556, which is the international standard for biodegradation of polyolefins, and the mesophilic conditions, then you got the 90%, you reached above 90% within 2 years, so in 266 days, that polyethylene film was able to reach more than 90%. All of our data is conducted by independent laboratories, so ISO 17025 certified laboratories. We don't do these, when it comes to our commercialization, we don't do kind of these tests internally. Internally, we only do research and development, but anything related to customers and to published data, it's always done by an independent lab, obviously because of the validity that this gives. Our portfolio ranges from flexibles to rigids, so as I said from the beginning, all of the standard plastics that we're all used to seeing in our supermarket shelves, so things like, cups, so this is, for example, one of our cups that is essentially 30% less plastic because it contains rice husk and it contains our technology in it. Your normal clear transparent cups that you see in festivals and street markets and everything. Fashion garment bags as well, ready to go packaging, so containers and lids and everything. And that's mainly it. So thank you so much for listening.